Hello, everyone, and welcome to the ultimate section of Cal 1. Let's graph functions. So, section 6.3 really brings everything together, sine tables, limits, and derivatives in order to create the graph of a function. So, what we're going to use to construct the graph of a function are 7 specific steps that I want you to follow if you have to graph a function. So every time we ask you to graph a function, implicitly, you need to follow these 7 steps. So here are the 7 steps. The first thing is you need to compute the domain of the function. You need to know where is this function defined. And we're used to that. We studied functions to their graphs or possible graphs before. And the first step before, just like right now, is to compute the domain of your function. And then the second step, very familiar step, is to compute any important limits linked to that domain. So for any open endpoints on your domain, you need to set up a limit and then compute its value. And of course, extract any visual information. If your function has any horizontal asymptotes, vertical asymptotes, or holes, it's really in step 2 that you're going to compute where your function has asymptotes. And asymptotes and holes are part of the graph of the function. Okay, so this is really very important step. It was important before. It's still important now for sure. Then the third step is to compute f prime and f prime prime, the first and the second derivative of your function. And then with those freshly computed formulas, the fourth step is to compute critical points of f and f prime. Here, be careful with the terminology. Even if we write down compute critical points for f and f prime, this is where the first and the second derivative are either equal to 0 or are undefined. So you are using the freshly computed formulas of step 3 to compute the critical points of f by using f prime and the critical points of f prime by using f prime prime, the second derivative. And now the most important step and the first 2 sections of that chapter was to set up this new step in the construction of the graph of the function. So construct the super sine table of f prime and f prime prime. And you're going to use that super sine table, which is basically just 2 sine tables together, one for f prime and one for f prime prime, where we're going to use the sine of the first and the second derivative to compute where is the function increasing, decreasing, and to classify critical points into local minimum and local maximum, or just increasing or decreasing points. And also, this is where we're going to compute where a function is concave up or concave down. And if there's any inflection point, this is in step 5 that you're going to see it. So the visual interpretation of the super sine table is basically what we introduced in section 1 and in section 2 of this chapter, the most important step of the construction. This is where you're using the theory, the connection between the sine table of f prime and the fact that a function is increasing and decreasing, or how to classify its critical points, and the sine table of f prime prime to get the concavity of f, and if there's any inflection point, this is where you're going to find it. So very, very crucial step. There's a reason why there's a star there. And then once you have the domain and the important limits and basically the shape of your function with step 5, you're almost ready to draw the graph. The first thing you have to do is just have some good starting point. You do this by first computing the y values of any points that you find in step 4. So these needs to be computed. So we're not looking for a precise graph, but we're looking for a graph where if there is a local min, local max, or an inflection point, they need to be clearly indicated on your Cartesian plane. And then if 0 is in the domain, computing the y-intercept will be a good contribution to the graph. If it's easy, finding the roots, find the roots of your function and then include them in your graph. So all that just to say, if there's any y-intercept or x-intercept, they should be on the graph. They're not mandatory step. I mean, if you forget about them, it's not too crucial. But if you have them, it will help creating the right graph for your function. And then 7th step is to actually draw the graph of your function. So in that step, you need to make sure to first start with the important points in step 6. If there's any horizontal, vertical, or holes for your function that you found in step 2, you should draw those first. right after. And then make sure that the graph you're drawing has the same domain, visually speaking, as the graph that you've computed in step one. And make sure that the shape of that graph is the same as the shape that we get from the supersine table in step five. So really always make sure that your graph is consistent with your solution. We're not looking for the right graph. We're looking for the graph that is consistent with your solution. This is way more important. All right, so now that I've gone through those steps, let's do an example where we're going to construct the graph of a function. So here we go. First example, let's construct a graph of the function x5 minus 5x plus 1. So this is a nice polynomial, no division, no square roots or no even roots, no logarithmic term. So this function, the first step, the domain is, poof, it's everything. So the domain is R, or the interval from minus infinity to infinity. So this means, of course, that there's two open endpoints. There's plus infinity and minus infinity. So there's two limits to set up and compute. So here we go. So you are going to poof, create the limit as x goes to minus infinity of x5 minus 5x plus 1, and the limit as x goes to infinity of x5 minus 5x plus 1. Remember, just defining the two limits linked to the open endpoints is what is this is the most important part of that step, just to define them. Now, these two limits are limits going to infinities of algebraic functions, so you can just keep the highest degree term. So this is like a trick that you can use. So if you have like an algebraic expression, you keep the highest degree term. So here between x5 minus 5x plus 1, I'm keeping 5x5. So this is the one that dominates. You can only use that trick if you are computing limits going to infinities. And same thing for minus infinities or plus infinity. So the limit of x5 minus 5x plus 1 is the same. This is just a trick you can use going to infinity. To the limit as x goes to minus infinity of x5, you replace x by minus infinity to the power 5 is minus infinity. So no horizontal asymptote, the function goes down forever as x gets larger, negatively speaking, and the limit as x goes to infinity of x5 minus 5x plus 1 is the same as the limit of x goes to infinity of x5. I'm just keeping the dominating term here. So you just plug in infinity, you get infinity to the power 5, which is infinite. No horizontal asymptote. The function goes up forever as x gets bigger to infinity. So these two steps, very familiar stuff. We've been like linking important limits to open endpoints domain for a while now. We're still using this. Okay, so we're using that experience from before to make it now complete. Now, step 3 and step 4. So step 3 here is just to compute the first and the second derivative. So for a polynomial here, so boom, the first derivative is just 5x4 minus 5. And then the second derivative is just 20x cubed. Remember, the second derivative is simply the derivative of the derivative. So step 3 is really just applying the rules typically of differentiation. Typically, these derivatives are easier to compute than the ones you have in a typical derivative question, but make sure that you compute them correctly because step 4 depends on it. Okay, so step 4, we need to find critical points for f and f prime. So here we go, poof, so 4, so here we, no, wait, where is it? So I'm going to use, so for critical points of f, you're going to use f prime. So here we go. So poof. So for f prime, normally you think about, is it possible that f prime is undefined? But in this case, 5x4 minus 5 is a polynomial. So you just set it up equal to 0. 5x4 minus 5 is equal to 0 when 5x4 is equal to 5. You divide by 5 on both sides. You get x4 is equal to 1. And then you take the fourth root on both sides because it's even. You get x is equal to plus or minus 1. So we have two critical points for f. It's when x is equal to minus or plus 1. Then you do the exact same thing with the second derivative. You want the first, not the case here. Is the second derivative crashing? No, 20x cubed will not crash. So you just have to focus on when is f prime prime equal to 0. Well, it's equal to 0 when 20x cubed is equal to 0. If you do the math, there's only one possibility. It's when x is equal to 0. Now, step 5, the most important step. So now we need to construct the super sign table. So here you take all the points that you just found in step 4, where the function f prime or f prime prime either crash or where they're equal to 0. And you construct a super sign table using these numbers. So here we have 3 important points, -1, +1, and 0. In order, the first one would be -1. Why is -1 there? It's there because f prime is equal to 0. So I like to write it down right away. Then 0. Why is 0 there? Because f prime prime is equal to 0. And there's also 1. Why is 1 there? Because f prime is equal to 0. And now we wonder what's going on with that function in between these 3 important numbers. So before -1, that's the interval from -infinity to -1. Between -1 and 0, that's the interval -1 to 0. Between 0 and 1, there's the interval 0 to 1. And then from 1 to infinity, or after 1, it's the interval 1 to infinity. And now we need to do a bunch of evaluations. So be careful with the super sign table. It feels like there's a lot of evaluation, but for f prime, there's only 3 evaluations: before -1, between -1 and 1, and after 1, just between the 0 or the undefined points of your sign table. So if I pick a number before -1, for example, if I pick -2, -2 to the power 4, that's 16 times 5 minus 5, that's going to be positive. So it's positive for before -1, so the function will be increasing. Now between -1 and 1, if I pick, for example, 0, 0 to the power 4 times 5 minus 5, it's going to be negative. So in one evaluation here, I get negative right through, and then after 1, if I pick 2, 2 to the power 4 times 5 minus 5, it's going to be positive. So I already know that my function is increasing from -infinity to -1. It's decreasing from -1 to 1, and it's increasing again from 1 to infinity. And implicitly, I also know that at -1, I'm going to get a local a local max, and at 1, I'm going to get a local minimum. But anyways, let's finish the sign table. So for the sign of f prime prime, I just need to do 2 evaluations, before 0 and after 0, on the function 20x cubed. If you pick a number before 0, for example, -1, -1 to the power 3 is negative times 20. It's negative everywhere. And then if you pick a number after 0, for example, 1, 1 to the power 3 times 20, that's going to be positive. Now my super sign table is filled up with the sign of f prime and the sign of f prime prime. Now it's time to do some visual interpretation for this. So here, what we're going to do is we're going to go under every single interval, and we're going to draw an arrow with the correct shape. And there's only 4 possibilities. It's either an arrow going up or down for increasing or decreasing. And we're going to add up concavity to that arrow. So it's going to be an arrow going up, curve upward or downward, or an arrow going down, curve upward or downward. So for every single interval in your super sign table, we have to draw an arrow. So between -infinity and -1. So here, I like to do these in steps because I'm not very smart. Okay, so here, first, I know because of the sign of f prime is positive that my function is going to be increasing. So I like to start with dotted lines. That just tells me that I need to draw something increasing, but then afterwards I'm going to include the shape of the concavity in this arrow. So I need to draw an arrow that is going up, but because of the sign of f prime prime being negative, it needs to be concave down. So there's only one arrow that is increasing concave down, and it's that arrow here. Now between -1 and 0, the sign of f prime is negative, so you need to draw an arrow that is going down, and then you will include concavity because the sign of f prime prime is also negative. There's only one arrow that is decreasing concave down, and that's the arrow you're looking for. And then, of course, what's going on at -1? Well, between these 2 arrows, you see the shape here. don't really need to think about it. Just look at it. You're on top of a little mountain. This is obviously an example of a local maximum. So you're on top of a mountain. You see the shape here. My function is increasing until -1 and then decreasing. That's a local maximum. Now between 0 and 1, my function, because of the negative sign in the sign for f prime, my function is still decreasing between 0 and 1. But now the concavity changes because of the plus for f prime prime. My function will be decreasing but concave up. So that's the arrow of decreasing concave up. So what's going on at 0? The function is decreasing right through, so it's not a local min or local max, but there's a change of concavity. So if there is a change of concavity, because there's a change of sign for the second derivative, well, that's by definition an inflection point. So 0 is an inflection point for our function. And then finally, for the last interval, my function f prime is positive, so I know my function f is going to be an increasing function. And then because the sign is positive for f prime prime, you need something that is increasing concave up. There's only one arrow here, increasing concave up, and that's that one. And then what's going on at 1, you can just see it. You're at the bottom of the bowl there. We have a local minimum. So here, that last row of the supersine table tells you everything. Like you can really feel the shape here. My function increasing concave down to a local max at -1, then decreasing concave down to an inflection point at 0, then increasing, it's still decreasing concave up until 1, which is a local minimum, and then it's increasing concave up forever after. Okay, so now we're almost ready to graph it. So the only thing you have to do here, you pick all 3 important points. So here, -1, 0, and 1. And what you do, you just compute output. So poof, here, I'm just going to give it to you. So here at -1, if you compute the output at -1, you're going to get 5. At 0, you're going to get 1. And at 1, you're going to get -1. So we have those. What about the y-intercept? Well, the y-intercept, we already have it here. It's the output at 0. The x-intercept, we have a function of degree 5, not easy to compute, so you don't worry about it. So now the moment of truth, time to draw the infamous graph of that function. So when you have to draw it on your own, make sure that the Cartesian plane that you're using, that the scale includes all the x values that you have in your step 6 and all the y values that you have at your step 6 also. So here I see I have my -1, my 0, and my 1, and my y values are ranging between -3 and 5. And I've already drawn the 3 points that I computed in step 6. Now let's connect the dot of that to create the graph. So here we're thinking about the shape that we found in step 5. So we know from step 5 that the function is first increasing concave down from -infinity to -1. So you draw this graph here of a function that is increasing concave down, reaching that point, -1, 5, that local maximum. And then between -1 to 0, the function is decreasing concave down and reaching that inflection point at 0, 1. And then the function is still decreasing, but now concave up all the way down to that local minimum at 1 minus 3. And then finally, the function is increasing concave up forever. Okay. And that's the graph for your function f of x. So I'm really using the shape of my function that I found in step 5. And when you are checking if your graph is correct, always think about these 3 important points. First is the graph of this function following the same domain. I can see here I drew this continuously over from -infinity to infinity, so same domain as step 1. What about the important limits? Well, we have 2 important limits. We had 1, which gave us -infinity when x was going to -infinity. And we see that this graph is consistent with that information. And we also found with the second important limit that the limit was going to infinity. And we see that this graph also goes to infinity, so it's consistent with that important limit. And of course, the shape is exactly the same as the shape in step 5. This is what you use to connect the points that you have in step 6. So always make sure that you double check the graph that you produce in step 6 and make sure that this graph is consistent with the domain and the important limits. And you're used to this. We've done this for a while now. The extra thing now is that we are connecting things using increasing, decreasing, local min, local max, inflection point, and concave up, concave down, and inflection point again. Sorry, I'm repeating myself. But anyways, for this first example of this graph, following the 7 steps to construct the graph of a function, it's a very nice example. It has everything in it. Both concavity, increasing, decreasing, there's a min, there's a max, and an inflection point. It's a nice little example to work with and to start learning the method. All right, for that video, for that first part of that section, that's it. That's all. Bye-bye.